Hello everyone, welcome back. In the previous video, I implemented a 4-bit counter, and now I'm going to upgrade to a 10-bit counter using a 32-bit pre-counter. So the design will remain the same, but here instead of using the 4 MSBs which I used for the 4-bit counter, I'll be replacing it to the 10 MSBs for the 10-bit counter and assign it to the 10 LEDs available on the FPGA board. So for the design, the counter design remains the same, where I'm using the reset, clock, and direction to control the counter for the 32-bit pre-count. So where reset, I've set it as an active low system, where on pressing the reset button, it will reset it to 0, or based on the direction button, it will either do up count or it will do down count. Once that is done, that will be the sequential part. Coming to the combinational part, the counter value will be updated to the 10 MSBs of the pre-count value, that is bit 22 to 31. So this is the only difference in the design compared to my previous 4-bit counter. So we'll go ahead and compile it. Once the compilation is completed, we can see the fitter report. Here you can see that we are still using 17 ALMs, 32 registers due to 32-bit counting, and 13 pins instead of 7 pins, where 3 pins are for the clock, reset, and direction, and 10 pins for the count. Once that is done, we can go for pin assignment. Using the pin planner, we'll be able to assign the location of the pins onto the FPGA board. So based on the data sheet, I've assigned the pins. That is, for count 9 to count 0, I've assigned the 10 LEDs, clock, reset, and direction. For reset, I've used the push button, and for direction, I've used the toggle switch. For clock, I've used the onboard 50 megahertz clock. For the design constraints, I'm reusing the same constraint where I'm providing the clock period of 20 nanoseconds to align with the 50 megahertz clock that I'll be reusing. Once the assignment has been done, we'll have to reconfigure or recompile the design so that the fitter or place and route part of the compiler will be able to compile or fit the modules based on the pin locations that I've just provided. Okay, so once the compilation with the pin placement has been completed, we can see there is not much changes to the ALMs. We are still using 14, 32 registers and 13 pins. Now let us go and program the device. Once we have the device connected to our system, we still see that the previous 4-bit counter is still working. This is because in our previous video we had flashed the onboard flash memory with our 4-bit counter. So even on system reset of the FPGA, the same bitstream configuration bitstream is used to configure our Cyclone 5 chip to run the 4-bit counter. Now let's go ahead and program the device for our 10-bit counter. So we'll click on auto detect. So now you can see in our previous video our devices were automatically detected since I was already tinkering on it. But in the last video I had added the flash over here, EPS128 for our flash memory. So when I reset it, so it became unknown. In order to select the proper device, I'll just click on auto detect again, and it will bring up a select device window. So here our board is 5C SEMA5, and I will select OK. So that brought up the proper configuration of the schematic. I'll go ahead and select my Intel or Altera Cyclone 5. I'm not sure why it is still being shown as Intel, even though Technically, Intel and Altera have separated. I'll just go ahead and select change file and select my respective SOF file. Once that file has been selected, I'll select program or configure and click start. Before that, here you can see on the board, it is still running the 4-bit counter. Once I click start and the configuration has been completed, it will immediately change to 10-bit counter. Whoa, that's a pretty fast counting. As you can see, it is using all the 10 bits or all the 10 LEDs to do the counting. Now it is doing up count since my configuration is in up counting. If I press reset, everything will be set to 0 and will start up counting. And if I toggle the switch to down count, immediately it will switch to down count. If I press the reset, it will go to 0 and then it will start counting down from all ones. To see the overflow, let me just do the up count. Now we are just waiting for all the LEDs to be occupied. Yeah, as you could see, it just went immediately to 0. Let's switch it to down count. And it will continue to do down count from whichever point I selected the down count. As you can see, it reached to 0 and overflowed to 1, all 1, the 10 bits of 1. So yeah, so that is the 10-bit counter with both up and down functionality and a reset button, reset functionality. As I had shown in the previous video, I can also configure this onto the flash memory so that when the reset happens of the board, it will still continue to do the 10-bit counting. To do the timing analysis, we will go to Tools, Timing Analyzer. We'll click on Update Timing Netlist. So that will basically read the STC file and all the netlist details to bring in to process. We'll go to datasheet, report Fmax, and we see that Fmax is 404 megahertz. We can see a hardly bump of roughly 10 megahertz, 10 to 13 megahertz in the Fmax. There is not much changes because our base system is still our base logic is still a 32-bit counter where only the MSBs are being used for the actual 10-bit or the 4-bit. In the 4-bit, we are just using the 4 MSBs. In 10-bit, we are using the 10 MSBs. Due to this minor change, we can see a slight modification or slight variation in the Fmax. To see the critical path, we'll go to report timing, and again we'll have to select the details over here. Basically doing a register to register evaluation instead of a port to port evaluation, since this is a sequential circuit or a sequential design. We'll just select the registers. Okay, 2 is also a register. Okay, and we are asking it to provide us the critical path or the path which has the most delay, and we'll click on report timing. Based on the design, it will bring up these constraints where the path between precount 12 to precount 28 is the most critical with a slack of 17.526 nanoseconds. Our design is made to run for 20 nanoseconds where each clock is 20 nanoseconds long, but our design is working within the 3 nanoseconds, and 17.5 nanoseconds is idle mode. So theoretically, our design will finish within around 3 nanoseconds, but since our clock is constrained due to the board's oscillator at 50 megahertz, it will stay idle for 17.5 nanoseconds. In the future, we can configure our device to run at a higher clock speed using the PLLs, where we can try to reduce the slack and get higher performance of the board. So yeah, this is it. A 10-bit counter using 32-bit pre-counter on an FPGA board. Thank you for tuning in. Thank you for watching this video. Hope this was informative and give you more knowledge towards this FPGA world. Thank you all. Have a great day.